14.6 Bernoulli equation. The outline of this video is as follows. We will begin by introducing the Bernoulli equation and motivating its importance in the study of fluid dynamics. This equation provides a powerful relationship between pressure, speed, and height for a moving fluid. Next, we will derive the equation step by step, showing how it emerges directly from the work energy theorem when applied to an element of fluid. With a solid theoretical understanding in place, we will then shift our focus to practical applications. We will first examine the Venturi tube, a clever device that uses pressure differences to measure fluid flow speed. Finally, we will explore Torricelli's law, a special case of Bernoulli's equation that describes the speed of fluid exiting an opening in a tank. This journey will take us from the fundamental concept to its real-world consequences. Bernoulli's equation is a key principle that connects the pressure, speed, and height of a moving fluid. It helps us understand many real-world effects that might seem counterintuitive at first. First formulated in the 18th century by Swiss physicist Daniel Bernoulli, this relationship applies to what we call an ideal fluid in motion. The central idea is that as a fluid flows, any change in its speed or its vertical elevation is directly linked to a change in its internal pressure. For a concrete example, consider the feeling of your car being pulled toward a large truck that passes you at high speed on a highway. This is not some kind of magnetic pull or suction. It is a direct consequence of Bernoulli's principle, where the fast-moving air between the vehicles creates a region of lower pressure. In short, the equation shows how pressure varies when a fluid's speed or elevation changes. To derive the relationship between pressure, speed, and height in a moving fluid, we will apply the work-energy theorem. Let us consider a segment of ideal fluid as our system. This system is non-isolated because the surrounding fluid exerts pressure forces on its ends, doing work and changing its energy. The fluid behind the segment pushes it forward, doing positive work, while the fluid ahead of it pushes back, doing negative work. The net work done on the segment is given by the expression W equals the quantity P1 minus P2, all multiplied by the volume V. According to the work-energy theorem, this net work must equal the change in the system's total mechanical energy. This means the work W is equal to the change in kinetic energy, which we call delta K, plus the change in gravitational potential energy, which we call delta U sub G. In short, the work done by the pressure difference is what causes the fluid segment's kinetic and potential energy to change. Now we can assemble the full work energy picture for our segment of fluid. The first step is to write down the change in the fluid's kinetic energy. This is simply the final kinetic energy minus the initial. The mass, m, of fluid leaving the segment has a speed, v2, and the same mass, m, entering has a speed, v1. So, the change in kinetic energy is 1/2 m times v2 squared minus 1/2 m times v1 squared. Next, we do the same for the gravitational potential energy. The change is the final potential energy minus the initial. This is equal to m times g times y2 minus m times g times y1. Finally, we substitute these two expressions into the work-energy theorem, which states that the net work done equals the change in kinetic energy plus the change in potential energy. This gives us the equation shown at the bottom, which relates the work done by the pressure difference to the total change in the mechanical energy of the fluid. We will now perform a final rearrangement of our work energy result to arrive at one of the most important equations in fluid dynamics. This process involves shifting our focus from the total energy of a fluid mass to the energy per unit volume. First, we take the entire work energy equation and divide each term by the volume, V. Then, we substitute the fluid's density, ρ, for the ratio of mass to volume, m, over V. This gives us an expression relating pressure, speed, and height in terms of density instead of mass. By rearranging the terms, we can group all the quantities at the initial position, point 1, on one side, and all the quantities at the final position, point 2, on the other. This elegant result is Bernoulli's equation. It states that the sum of the pressure P, the kinetic energy per unit volume 1/2 rho, V squared, and the gravitational potential energy per unit volume rho gy remains constant along a streamline. In short, Bernoulli's equation is a statement of the conservation of energy for an ideal fluid in motion. Bernoulli's equation gives us three powerful insights into how a fluid's pressure changes with its motion and positions. First, and perhaps most famously, the equation shows that as a fluid's speed increases, its pressure decreases. This is known as the Bernoulli effect. For example, when a large truck passes your car, the air is forced through the narrow gap between the vehicles, making it speed up. This faster-moving air has lower pressure than the air on the other side of your car, creating a net force that seems to pull you toward the truck. Second, the equation tells us that as the elevation of a fluid increases, its pressure decreases. This explains why water pressure is often lower on the top floors of a tall building compared to the ground floor. Finally, if we consider a fluid that is at rest, the velocity terms in the equation become zero. In this static case, Bernoulli's equation simplifies to the familiar formula for hydrostatic pressure we have seen before, where the pressure difference is equal to rho times g times h. This shows that Bernoulli's equation is a general principle that also covers static fluids. This quiz provides a great, intuitive way to see Bernoulli's principle in action. Let us think through the physics, step by step. Initially, the two balloons are at rest, so the air pressure on all sides is the same. When you blow air into the narrow gap between them, that air is forced to speed up as it passes through the constrictions. According to Bernoulli's principle, where the fluid speed is higher, the pressure is lower. This means you have created a region of low pressure between the balloons. The air on the outer sides of the balloons is still relatively stationary, so it remains at a higher atmospheric pressure. It is a common misconception that blowing air at something always pushes it away. Here, it is the pressure difference that matters. This pressure imbalance creates a net force pushing each balloon inward, from the area of high pressure toward the area of low pressure. Therefore, the balloons will move toward each other. Now let us look at a practical application of Bernoulli's principle called the Venturi tube, which is a clever device used to measure the speed of a flowing fluid. We start by applying Bernoulli's equation between 2 points, the wider section, point 1, and the narrower, constricted section, point 2. A key feature of the Venturi tube is that it is horizontal, meaning the height y1 is the same as the height y2. Because the heights are equal, the gravitational potential energy terms on both sides of Bernoulli's equation cancel out. This leaves a simplified relationship connecting only pressure and speed. P1 plus 1/2 rho, V1 squared equals P2 plus 1/2 rho, V2 squared. This equation has two unknown velocities, V1 and V2, so we need a second equation. We get this from the equation of continuity for an incompressible fluid, which states that A1 times V1 equals A2 times V2. By rearranging this, we can express V1 in terms of V2. With these two equations, we have set up the physics needed to solve for the fluid's speed. Our goal here is to combine our two main equations to solve for the unknown fluid speed, V2. We start by taking the expression for V1 from the continuity equation and substituting it into the simplified Bernoulli equation for the horizontal pipe. This is a crucial step because it leaves us with an equation that has only one unknown speed, which is V2. The rest of the process is algebra. We rearrange the equation to group all terms containing V2 squared on one side and the pressure difference, P1 minus P2, on the other. After factoring and solving for V2, we arrive at the final expression shown. This equation is the main result for a Venturi tube. It provides a practical way to determine the speed of a fluid by measuring the pressure difference between 2 points and knowing the cross-sectional areas of the tube at those points. To find the exit speed of the liquid, we will apply Bernoulli's equation between two specific points, point 2 at the top surface and point 1 at the exit hole. First, let us establish the conditions at each point. At the top surface, because the tank is very wide compared to the hole, the liquid level drops extremely slowly. This allows us to make a very good approximation that the speed of the fluid at the top, V2, is essentially 0. Next, consider point 1, right where the liquid exits. Since it is flowing into the open air, the pressure at this opening must be equal to the surrounding atmospheric pressure, which we label as P0. It is important to distinguish this from the pressure P of the air maintained above the liquid inside the tank. Finally, the height difference between the surface and the hole is given as h. With these key assumptions, we can now simplify Bernoulli's equation to solve for the exit speed, V1. Let us now apply Bernoulli's equation to solve for the speed of the liquid as it exits the hole. Equating the conditions at the hole, point 1, with the conditions at the liquid surface, point 2, gives us the expression shown. Remember, P0 is the atmospheric pressure at the exit, while P is the pressure of the air inside the tank above the liquid. When we algebraically rearrange this equation to solve for the exit speed, V1, we get a general result. The speed equals the square root of the quantity 2 times the pressure difference, P minus P0, all divided by the density ρ, plus the term 2 times G times H. Now consider the important special case, where the tank is open to the atmosphere. In this situation, the pressure P at the top of the liquid is the same as the atmospheric pressure P0. This causes the pressure difference term in our equation to become 0. The equation simplifies dramatically, giving us Torricelli's law. The exit speed, V1, is equal to the square root of 2gh. This result means the speed of the liquid exiting the hole is exactly the same as the speed an object would have after falling freely from rest through a height h. Now let us consider a classic follow-up question. If this tank is open to the air and sitting on a table, where should we place the hole to make the water stream travel the farthest horizontal distance? This is an excellent problem that combines fluid dynamics with projectile motion. Once a parcel of water leaves the hole, its path is determined by 2 factors: its initial speed and its time in the air. First, its initial horizontal speed comes from Torricelli's law. This speed depends on the depth of the hole, which is the water surface height, y2, minus the hole height, y1. So the velocity is the square root of the quantity 2 times g times the quantity y2 minus y1. Second, the time of flight depends only on the vertical distance the water falls, which is the height of the hole, y1. From kinematics, this time is the square root of the fraction 2 times y1 over g. The horizontal range, xf, is simply the horizontal speed multiplied by the time of flight. This gives us an equation for the range that depends only on the position of the hole. Notice the trade-off. A low hole gives high speed but a short flight time, while a high hole gives a long flight time but low speed. Our goal is to find the height y1 that maximizes this range. We now have an equation for the horizontal distance the water travels. Our goal is to find the height of the hole, which we call y1, that makes this distance as large as possible. The formula for the range depends on the square root of the quantity y1 multiplied by the quantity y2 minus y1. To maximize the range, we simply need to maximize the function inside that square root. This is a classic calculus problem. We find the maximum value by taking the derivative of this function with respect to y1 and setting the result equal to 0. The derivative works out to be y2 minus 2 times y1. When we set this equal to 0 and solve for y1, we find that the optimal height is exactly 1/2 of the total water height, y2. This result represents a perfect balance. A lower hole gives a higher exit speed but less time in the air. A higher hole gives more time in the air but a lower exit speed. The maximum range occurs exactly in the middle. Therefore, to make the water travel the farthest, the hole should be positioned halfway between the bottom of the tank and the surface of the liquid. To wrap up our discussion, let us summarize the core concepts of Bernoulli's equation. At its most fundamental level, this equation is a statement of energy conservation, but specifically tailored for an ideal fluid in motion. The equation states that the sum of P plus 1/2 rho V squared plus rho G Y is constant along a streamline. Each term has a physical meaning. P is the static pressure. The term 1/2 rho V squared represents the kinetic energy per unit volume. The term rho Gy represents the potential energy per unit volume. The most important practical consequence of this equation is the inverse relationship between fluid speed and pressure. Where the speed of the fluid is high, its pressure is low, and vice versa. This principle has wide-ranging applications, from generating lift on airplane wings and measuring flow with venturimeters, to explaining how fluid exits a container, as described by Torricelli's law. In short, Bernoulli's equation provides a powerful connection between pressure, speed, and height in fluid dynamics. To wrap up, let us consider 2 review questions that apply the concepts we have just discussed. The first question asks about the air pressure on the top and bottom surfaces of an airplane wing. To generate lift, the wing is shaped so that air travels faster over its curved top surface than its flatter bottom surface. Using Bernoulli's principle, consider what this speed difference implies about the air pressure above and below the wing, and how that creates an upward force. The second question is a follow-up to our example on Torricelli's law. It asks you to find the position of a hole in a tank that maximizes the horizontal distance the water travels. This is a classic optimization problem. You will need to combine Torricelli's law, which gives the initial horizontal speed of the water, with the equations for projectile motion. Take a moment to pause and work through these problems, as they are excellent practice